All right, welcome back. So now what we're getting into, the final section out of chapter 3 that we're going to see here before our exam that we're taking this coming week, of course, depending on hopefully whenever you log into this video. Final section is what's called the fundamental theorem of algebra. So something pretty important. So this is probably the culmination of all the excitement that you could possibly imagine all throughout any algebra course. I'd recommend sitting down throughout this lecture, but you are only going to need the edge you see for this one. So what I'd like to stress as we go in here, there's going to be some notes I want you to pause and jot down at the beginning here between these two boards. What I want to stress is that there is really nothing new in this section at all compared to what we've done throughout the entire chapter. This really combines all of our ideas together, whether that be division, finding x-intercepts, finding real roots, so those tests we've done, potential real roots, number of positive and negative, Descartes' rule of signs, and complex numbers. And now that we combine complex numbers in with real numbers, the fundamental theorem of algebra says this. Every polynomial that we study that has a degree, just saying, of at least 1 or higher, so highest exponent 1 or higher, it has exactly the degree n roots if we involve the complex and imaginary numbers. So meaning, before we would say that the degree is equal to the maximum number of real zeros or intercepts, but now that I involve the complex numbers, the big takeaway here is whatever the degree is, that is how many solutions or zeros I have to get. So again, moving on to this second board here, and again, take a minute, pause, jot down everything I have here, and then I'll give a quick explanation of what's up here. Just some things to keep in mind throughout the course of this section. First, every polynomial, I know that I am finished simplifying, going through any factoring and any synthetic division that I need to when I see all linear or quadratic factors. So highest power 1, highest power 2. Secondly, if the degree is odd, just again something to keep in mind, if I have an odd degree, highest power, I will always get at least one real solution, always. With an even degree, I may or may not get that, and hopefully you can visualize and think why that would actually be the case. So again, if we have an odd degree, I have to get a real solution, at least one, I might have more. And finally, just another note that'll be used in some problem solving, so I definitely make a note of this here. It's a real quick shortcut, kind of quick theorem. Complex and imaginary solutions that I find, so anything that involves the square roots of negative numbers, they must always occur in pairs, conjugate pairs. And conjugates, if you need a refresher there, they're the opposite signs of the term. So if 6i is a solution, it means that negative 6i must also be. Think about taking the square root of negative 36 in an equation. That would be where you get that, positive and negative 6. Or another example of a binomial conjugate, if 3 minus I is a solution, that means 3 plus I must also be a solution. So again, jot those down, re-listen to my explanations, particularly with a couple of those shortcut tips there, because those could be used in some quick answer problems on quizzes or exams moving forward. So all we're going to see today then is just a couple of examples, and I'd recommend you try these on your own too. You will know theoretically how to solve them. You will know how to solve them. Check your work at the end. Again, you're going to see no new techniques here. First one, f of x is equal to x to the 4th minus 1. Now this is going to be a pretty straightforward one because I can factor this right away. This is a difference of squares. Another thing to keep in mind, I am going to get 4 solutions. I may see a mixture of imaginary and real, or maybe one or all of one anyway, but I must now get 4 solutions once I have gone through all of my process. So as always, to solve a quadratic, not a quadratic, but a polynomial, I'm finding it's 0, so I'm filling 0 in for y. As I mentioned, this one is factorable. This is a difference of squares. This would factor as x squared plus 1 times x squared minus 1. Okay? Now next part, this is unfactorable. A couple of mistakes I saw in the last quiz are people trying to factor things with sums of squares. This is unfactorable, which means that I'm going to get my 2 imaginary solutions here anytime I end up involving square roots and negatives, and you'll see where that comes into play. This part, however, I can factor. It's just another difference of squares. And this would be x plus 1 and x minus 1, giving us two real solutions, positive and negative 1. So again, there's two of them. The other two solutions we are going to get out of this quadratic factor. I simply set it equal to 0. Saw a pretty quick one like this on the last quiz and also in the notes from the last section. Subtract 1 from both sides. I get x squared equals negative 1. Simply take the square root of both sides, and because we're taking the square root of a negative, that's where we get imaginary values. And always plus and minus. Square root of negative 1 is just defined as I. So what you can see here, at the end we got four solutions. Two imaginary, positive and negative I, two real, positive and negative 1. So what I'll stress is if you can factor, do that right away. It's always going to be the quickest route to solving these problems. Second one. Now what I am going to do for this one, I'll be a little more detailed with this one compared to the second one, or I'm sorry, compared to the last one that we're going to do today. X to the fourth plus 2x cubed plus 10x squared plus 18x plus 9. Okay, so what I will stress, look for factor by grouping if you can. That's used when there are four terms. However, I would make a note of this. Anytime you have more than four terms, and you can see we have 5, any more than 4, you have to use synthetic division to get your polynomial more reduced than what it is at the beginning. So once again, just like the last one, I know I must get 4 solutions, have to. The other thing, let's go through some other concepts from the last couple of sections. Let's use Descartes' rule of signs to figure out what types of roots to look for. Okay, so what I do remember, f of x, I go back and I count the sign changes. So, oh, no change, no change. Hopefully you can see the whole polynomial is positive at the beginning. So 0 sign changes means that I will get 0 real positive roots. Okay, so again, this was something else, and this is part of why I want to go through part of this here anyway. A lot of people mixing up this rule on the last quiz. Remember, Descartes' rule of signs means I count the sign changes. It tells me how many positive and negative roots that I will get that are real. Finally, remember, I also have to do f of negative x to count the negative roots. So I fill in negative x to the fourth plus 2 times negative x cubed plus 10 times negative x squared plus 18 times negative x plus 9. And once again, I'm just going to use properties of exponents to evaluate negative to an even is positive, plus this would be, well, actually I'm going to leave the sign off there for now. Negative cubed would be negative, so this will become a negative 2x cubed. Negative squared, once again, is positive. 18 times negative x would be minus 18x plus 9. So now you can see we do have a bunch of sign changes happening here. There's 1, 2, 3, and 4. So remember what this tells us. 4 sign changes implies that we will get 4 possible real negative roots or even number less. So that could be 4, 2, or 0 real negatives. All right, I'll leave that board. I'm going to come back to that. That'll be important later on to save us a little time. Next, remember what we do next. We must find all potential roots. So we run the rational root test. What are my factors of p, q, and p over q? Remember, factors of p are the factors of the constant, so that would be plus and minus 1, plus and minus 3, plus and minus 9. Factors of q, factors of the leading coefficient. So in this case, it's just 1. Finally, p over q. Anytime q is just 1, it's always just the original list from p. All right. So next part. The next thing I have to do is using one of my rational roots, one of my possibilities from this list, I now have to use synthetic division to reduce the polynomial. So remember, I'm trying to find its factors. Okay. Now remember, I go back to this list. Any combination of these may be my final solutions, my x-intercepts, my roots. So again, I think probably human nature and the way we usually do these problems, people think, all right, well, might as well start at +1. That's an easy one to do. I'm going to kind of back up here for a second. I'm going to say I have no need to test +1. I know it's not going to give me, it will not be a factor. It will not give me a remainder of 0. Think about that for a second. Why will I not bother testing 1? The reason for that, this is why we do Descartes' rule. It's not just some weird, obscure concept. I found in Descartes' rule that because there are no sign changes, I will not get any real positive roots. Why bother testing any of the positives then? So what I'm going to do then, let's test -1. So we're going to set up our synthetic division process. Okay, so across the top, remember, go the coefficients from the original. So it's going to be 5 of them in this case. It'll be 1, 2, 10, 18, and 9. All right, and once again, hopefully the synthetic division process is pretty straightforward at this point. I drop my first one down. -1 times 1 is -1. 2 minus 1 is 1. -1 times 1 is again -1. 10 minus 1 is 9. -1 times 9 is -9. 18 minus 9 is 9. -1 times 9 is -9. So we do get what we anticipate. 9 minus 9 is 0. Remember, refresher from last section, remainder of 0 means that -1 is a solution. And also, remember, this makes x plus 1 a factor, which is very important because now I'm going to have to go farther. Okay. So remember, and I'm going to leave this here for reference, I can take out a factor of x plus 1 because -1 was going to be one of my solutions. I know that now. And what I do is I write, remember, these are the coefficients of the new polynomial with the degrees decreased by 1. So that becomes a 1x cubed plus 1x squared plus 9x plus 9. Okay. Now remember, you have a couple of options at this step. You can, if you want to, go back to your list. Maybe try a different value. Try a different negative number. It may or may not work, however, because those might not be solutions. What I would always recommend is once you get to 4 terms, think factor by grouping. And this one is going to work out by grouping. So remember, what I do then is I think I can take an x squared out of the first group, and I'm left with x plus 1. I can then take out a 9 from the second group, and I'm left with x plus 1 again. So again, I always like to emphasize with factoring by grouping, I'm kind of just taking out a GCF again from both of these whole terms, which is another x plus 1 factor, and I'm left with x squared plus 9. So hopefully you can see what we're going to get here. I actually have a repeated solution, -1, so that's going to be a real number. X squared plus 9, I'm going to get 2 imaginary solutions, once again because of the sum. So I just simply do x squared plus 9 set equal to 0, subtract 9 from both sides, square root of both sides, always plus and minus, square root of -9 is 3i. Okay, so now you're saying, well, wait a second, we got 3 solutions, positive, negative, 3i, which makes sense, right? Because we have our 2 conjugate imaginaries, but I only got 1 more real solution, which was when we should have gotten 4. remember, it all goes back to this. We had a repeated factor. So effectively, 1 is used twice. The math technical way to say it is that 1 has a multiplicity. I'm sorry, this is negative 1. My apologies there. X plus 1, the solution we got was negative 1. The solution negative 1 has a multiplicity of 2. How exciting is that? So essentially that accounts for 2 of our solutions, so giving us our grand total of 4. So again, that is the full shooting match. You know, how do we find these solutions? All goes back to the ideas that we are now combining within this section. All right, so the last one, and I'll go a little quicker through this one, but I'll give you the work, of course. Of course, throughout, I would recommend you try this one on your own. Go through the exact same setup that I just did. F of x is equal to x to the 4th minus x cubed plus x squared minus 3x minus 6. So again, I'd take a pause right now, try it, go through Descartes' rule, rational root test, and then synthetic division to try and narrow down your choices and factor. Okay, so pause it, try it. Now I'm going to go through the solution in those parts anyway. Okay. So the rational roots, hopefully you found. And again, Descartes I'm going to gloss over for now personally, but it's just, again, count the sign changes, tells you the positives, find f of negative x, and count the negative sign changes also. Just to get our P over Q list here, say potential, that's going to be ending up to be the factors of 6. Okay. All right. Now, just for the sake of, well, actually, I'll show you one that doesn't work here. Just in case you get in this predicament. Again, we kind of always think, all right, well, let's try the easiest number to work with first, which is 1. So let's see what happens when I use 1. 1 times 1 is 1, I get 0. 1 times 0 is 0. 1 plus 0 is 1. 1 times 1 is 1. Negative 3 plus 1, negative 2. 1 times negative 2 is negative 2. When I get a remainder, that means 1 is not a solution. I essentially throw that out right there just to show you what that looks like. Let's now try negative 1, and I do know that negative 1 works. So once again, to go through, put our coefficients up top. Okay, it's 5 of them, so I drop 1 down. I get negative 1 times 1 is negative 1. Negative 1 minus 1. Careful, just with the little arithmetic going through. That can, of course, throw your whole rest of the problem off. Negative 1 and negative 2 is 2. 1 plus 2 is 3. Negative 1 times 3 is negative 3. Negative 3 minus 3 is negative 6. Negative 1 times negative 6 is 6. And sure enough, there's our remainder 0, like we're expecting there. So again, that makes x plus 1 a factor. And now let's continue, just like we did in the last question. So I can make f of x equal to x plus 1, the factor we just found, and use these 4 coefficients to write the remaining polynomial, decreasing the degree again by 1. So that's going to leave us with x cubed minus 2x squared plus 3x minus 6. Again, hopefully these patterns will start to jump out at you. 4 terms I want to factor by grouping to get the remaining solutions. Okay. I can take an x squared out of the first 2 terms. I'm left with x minus 2. Second set of terms, I can take a plus 3 out. Once again, we're left with an x minus 2 factor. When I undistribute or take out that x minus 2 factor once again, we can now clearly see 2 of our solutions, and they're going to be real numbers. Okay, and again, always think, when I get an x squared plus a number, that's always going to be 2 imaginary solutions. So my first 2 are negative 1, which we found earlier, positive 2, because that's the value that makes that factor equal 0. And then over here, hopefully you can kind of get used to seeing these also. Always set equal to 0 though and solve if you're unsure. When I take the square root of both sides, all I'm going to do is, as always, plus or minus, think of just taking the square root of -1 out, which is I. 3 is a prime number, so I can go no further. So now I'm getting kind of low there. The solution with that, just leave the square root of +3, take the I value out front so that we can clearly see it's a simplified imaginary number. So, as we expected, 4 solutions. In this case, there were 2 reals, 2 imaginaries, plus or minus I radical 3. So, again, there's the culmination of the chapter. There will be, as usual, an assignment. Make sure you try the exam review sheet, and that's it for the chapter. So again, finding all zeros of polynomials, and that's it.